everybody, this is the last section of chapter 5, 5.7, and here we are going to look at reversing all of our inverse trig functions, anti-deriving exponentials with base b, as well as looking at ln's, natural logs. So as your warm-up, I'm not going to actually fill this in for you, but it's just a refresher trying to recall all of the derivatives of your trig inverse functions, because when we go to our antiderivative, of course, we're going to be using these. So I have them filled in here for you. The derivative of sine inverse, remembering it's 1 over the square root of 1 minus x squared, etc. So now when we look at integral problems, the right-hand side of these equations are what's going to be inside of the integral, as you can see on the right here. The reason only 3 of the 6 of them are here is because remember that the others were just negatives. So we don't actually have to use those. We can always just apply the negative instead. So first example, integral up from 0 to 1, dx over x squared plus 1. So sometimes the challenge is, well, how do I even know that it's inverse trig rather than just a regular u sub? Well, if I were to start with a u sub, I'd probably pick my denominator. Right away I get to a du that has a 2x in it. I don't have either of those in my numerator, so I don't have enough to replace things. So that's when I have to start thinking about, okay, what else could this be? And I want to recognize that this is my tan inverse pattern. So there's nothing to substitute here. This is a direct integral to tan inverse of x from 0 to 1. So tan inverse of 1 minus tan inverse of 0. So tan equals 1 at pi over 4, and tan equals 0 at 0. So therefore the answer here is going to be a pi over 4. Now this example, right? So we need to recognize that this is going to be the secant inverse. Okay, there is a term on the outside of the square root underneath. It's an x squared minus 1 underneath of it. So the most important thing here, this is also kind of a u sub, is we need to make it fit the exact pattern, right? The exact pattern says this, 1 over x, square root of x squared minus 1. Okay, so we need to, first of all, write what's underneath the square root, the part that's being squared, as a quantity. That's always going to be your first step. So I can rewrite 4x squared as 2x, quantity squared minus 1. Okay. Whatever ends up being inside of those parentheses or being squared, that becomes our u. So u equals 2x, du equals 2 dx. Okay. We know that we have that extra x in this problem by the nature of a secant inverse, so x equals 1/2 u. We want to change our limits of integration just like in the previous section, so u of 1 over root 2 equals, and u of 1 equals. So our u is just 2x, so we get 2 over root 2, which would rationalize to just a root 2, and we get a 2. Okay, so now substituting back into our integral, we're going to have the integral from root 2 to 2. We're going to have dx is equal to 1/2 du. Right, I didn't write that over here. So I do a direct plug-in for dx. I do a direct plug-in for x, which is 1/2 u. And then I have the square root of u squared minus 1. Okay, so my 1/2s do cancel out. I don't actually need them, but again, I like the method of just doing a direct substitution. And now I have exactly the secant inverse pattern. So secant inverse of u from root 2 until 2. Evaluate these. Okay. Remember, secant is the reverse or the reciprocal of cosine. So I'm kind of thinking, when is cosine? 1/2. And that happens at pi over 3. And the root 2 would happen at pi over 4. So that would be pi over 12. Okay, our next example. Again, first things first, recognizing which trig inverse do we have? So I don't have anything out in front of the square root this time in the denominator. I have a 1 minus x squared, so I have my sine inverse. Okay, but it does look a little bit different, right? So I don't even have a 1 in my denominator now. I have a 9, and I have to take care of that. So always take care of underneath your square root first. It has to look like that 1 minus x squared or 1 minus u squared. So my first thing is to kind of change that. So I'm going to factor the 9 out. It helps that this 9 is a perfect square, but it doesn't have to be. So if I factor 9 out, it becomes 1 minus 16/9 x squared. I can take the 9 completely out, turn it into a 3. And again, I need to write this as a quantity squared. So 16/9 x squared quantity squared would become 4/3 x. Okay, so that's your first step, right? That allows us to identify what is the u. So the u is 4/3 x. du is 4/3 dx. dx is then 3/4 du. And x is also 3/4 u. u of 0, u of 3/4 has to be done. Right? Every single part of the integral has to become a u. So u of 0 is still 0. u of 3/4 is 4/3 times 3/4 is 1. Okay, so now I can go back, rewrite my integral. So the dx becomes a 3/4 du. I do have that 3 out in front, which is fine. Square root of 1 minus u squared. Okay, the 3/4 and the 3 that's out in front, it doesn't matter. It doesn't impact your sine inverse. You can pull that out of the integral entirely or just integrate from here. That doesn't matter. So this becomes a 1/4 sine inverse u from 0 to 1. So sine inverse happens at 1, at pi over 2, and 0 is 0. So we get a pi over 8 for our answer. So I'm going to leave the next two for you to practice. We'll do it together in class, and you can try it on your own now. Okay, identifying which trig inverse you have to match. Okay, and then using u substitution along with it. And next I want to do an example with our exponential. So the exponential functions essentially were linear chain rules, right? Because we had to multiply by that lnb, which was just a coefficient. So now we're going to divide the lnb out. Okay. So that means in this particular case, I do not have a u sub. All I'm doing is if I integrate the 7 to the x stays, and I divide out the ln 7. Because if I were deriving this, I would be multiplying by an ln 7 from 3 to 5. So to get an actual numerical answer, of course, I would have to go to my calculator. Most of the time, I would just prefer the answer like you see it here, but I'll give you the decimal answer from the calculator. Okay, so if this was in conjunction with a chain rule, like this. Again, the function that I'm looking at here, the main function here is that exponential, right? I have trig in there, but I know that I'm going to have to deal with it. So it is a u sub, right? Start by picking your inside. So u is equal to sine theta, the exponent. du is then cosine theta d theta, which is a perfect match for everything that we have. U of pi over 2 becomes, and u of 0 becomes, so sine at pi over 2 is going to be 1, and sine at 0 is 0. So everything swaps out perfectly. Integral from 0 to 1. The cosine theta d theta gets replaced with the du, and 10 to the u power. So now we just follow our exponential rule, which says 10 to the u, divide by ln 10, integrate from 0 to 1. So 10 over ln 10 minus 1 over ln 10, which would be 9 over ln 10. Okay. One more example on these notes. Again, I'm going to leave this for practice together, and that is it for Chapter 5.